All right, so you've done the work, you've crunched the numbers, and you've got this beautiful line of best fit running through your data. Awesome. But how do you really know if that line is telling you the truth? Or is it just a convenience story? Well, today, we're going to give your model a proper diagnosis and find out for sure.
It's so easy to just glance at a scatter plot with a regression line and think, yeah, that looks about right. But you gotta be careful because looks can be really deceiving. Just fitting a line to data isn't the end of the story. We have to be sure the model itself is fundamentally sound. It's kind of like this. Just because a doctor prescribes a treatment doesn't automatically mean it's the right one for the patient, right?
So, to figure out if our model is healthy, we're going to play Data Doctor. We're going to run 3 essential diagnostic tests. And by the end of this checkup, you'll know for sure if your model is in great shape or if it needs some serious intervention. Okay, test number 1. Think of this like checking a patient's most basic vital sign. We need to measure the model's overall strength and see how much heavy lifting it's actually doing. This is all about its explanatory power. And the tool we use for this has a fancy name, the coefficient of determination, but you probably know it as R-squared. All it does is answer one simple question. How much of the story in our data does our line actually explain? It's just a percentage that tells us how much of the change in our y variable can be chalked up to our x variable. And check this out, it's actually pretty straightforward. Let's say our correlation coefficient, r, is 0.85. To get r-squared, you just square it. That gives us 0.7225. So what does that mean? It means our model explains 72.25% of the variation in the data. Pretty good. The other 27.75%? Well, that's just unexplained. It's variation caused by other stuff that's not in our model. Now that's a good start, but our checkup is definitely not over yet. A good r-squared value feels great, but it can be hiding some serious underlying problems. So for our second test, we have to dig a little deeper and look for any hidden symptoms. It's time to see if there are any sneaky patterns that our first test might have missed. And how do we do that? We look at the leftovers, the residuals. A residual is just the error. It's that little vertical gap between what the line predicted and where the data point actually is. And when we plot all of those errors together, we get a residual plot. That's where the secrets about our model's health are hiding. So, the first clue we're hunting for is a pattern. A healthy residual plot should look like a random mess, like a shotgun blast of points with no rhyme or reason. But if you see a distinct U-shape or any kind of curve, that is a major red flag. It's a clear symptom that the relationship in your data isn't linear to begin with, and using a straight line model was just the wrong call. The second symptom we're checking for is the spread of those leftovers. In a healthy model, the errors should be pretty consistently scattered around. There's a fancy word for this, homoscedasticity. But if you see the points fanning out into a funnel or a cone shape, that's a problem. That's called heteroscedasticity, and it means your model is getting less and less accurate as you move along the x-axis. Its predictive power just isn't consistent. Okay, we've checked the model's overall power, and we've dug around in the errors for hidden patterns. For our final test, we need to check for any single data point that might be throwing the whole system out of whack, a point that's skewing our entire diagnosis. We call this an influential observation. And seriously, think of it like one extremely unusual case that's literally pulling the entire line of best fit towards it. If you were to take out just that one point, the slope or the intercept of the line would change, and change dramatically. It's an outlier that has some serious muscle. But here's where it gets a little tricky, because not every point that looks extreme is actually influential. So we have to ask, what's the real difference between a point that could have a big impact and one that actually does? This is the crucial distinction between leverage and influence. Let's break this down. A point has high leverage if its x value is way out there, far from the average of all the other x values. It's an outlier on the horizontal axis, which gives it the potential to yank the line around. But it only becomes truly influential if it's also way off the general pattern of the rest of the data. See, a high leverage point that just happens to fall right where the line was going anyway, it's not influential. The really influential ones have both high leverage and they're way off the beaten path. And that's it. The checkup is officially over. We've run all 3 diagnostic tests, and now we are ready to make a final and much more informed diagnosis on the health of our regression model. So let's just boil this all down into your own personal diagnostic toolkit. It's a simple 3-step process. First, check your R-squared for its overall explanatory power. Second, you've got to analyze your residual plot for any of those lurking patterns or weird-looking spread. And third, identify and really investigate any points that might be influential and warping your results. And here's the bottom line. A truly reliable, trustworthy, healthy linear model, it's not just about getting a high R-squared. Nope, it has to pass all three of these diagnostic tests with flying colors. It needs to have solid explanatory power, totally random residuals, and no single point pulling all the strings. So, the next time you see a line of best fit somewhere, don't just take it at face value. You now have the diagnostic tools to pop the hood and question what's really going on. So the real question is, what truths, or, maybe what convenient fictions are you going to uncover in the data all around you?